Data Skeptic is the official podcast of dataskeptic.com, bringing you stories, interviews, and mini episodes on topics in data science, machine learning, statistics, and artificial intelligence.
All right, Linda. Today we're going to talk about a particular type of neural network architecture that we're going to define by what it isn't. And it is neural networks that do not have cycles, no feedback loops. Now, you're comfortable with, at least at a conceptual level, what a neural network is, right? Or no?
Can you remind me?
We have a neuron, which is this sort of object. It has a bunch of inputs. And then depending on what the inputs are, it has an output. And that a network is a construction of all these things that somehow, somewhat magically, converts some input into some decision or some output. So like image recognition is the classic example. The inputs are all the pixel intensities, which, from a mathematical point of view, they're just random numbers. Well, not random, but they're numbers. And then some kind of way, the thing is able to be like, oh, that's Linda. Facial recognition. Pretty impressive, right?
So how's that different from machine learning?
Neural networks are a subset of machine learning. They are a particular data structure that you use for machine learning.
And how's it different from AI?
Well, that's pretty... First, give me your definition of AI, and then I'll answer your question.
I don't know. People have it on their resumes.
Okay.
So if there's no definition, why do they put it there?
I don't know. Recruiters call you and you get jobs?
I should throw that on mine.
Yeah, go for it.
Project manager of AI.
All right, so let's appeal to your project management for a minute when we talk about feed-forward neural networks. You've done a little bit of like industrial manufacturing type stuff, have you not?
Well, from working at Dollar Shave Club, they do things in mass sometimes.
And what's the process like there? Do you just wake up in the morning, decide you want to have a product, and by the end of the day you got a prototype?
Well, manufacturing in general, the lead time is really long. Some things, if you just buy them out of the box, pre-made, or they already have the capabilities to make them, that'll have a faster turnaround time than if you want something custom made.
For example, like lotion. I bet if we went to the store right now and looked at different lotions, a bunch of the bottles on the shelf from different companies all have the identical chemical thing inside, right?
Well, I was just talking about bottles. So if you go to the shelf of lotions, you can see some of them have the same bottle.
Oh, yeah, even the same bottle, too, with different products inside. Are you familiar with the waterfall model of design?
Design? I just know project management. It just means you get to one step, then you can move forward to the next step.
Yeah.
And you move forward to the next step. And generally, you try, well, I was just saying all of project management or leading a project. The goal, if you want to save time and money, is not to change the scope.
Yeah, so you can't go backward. Once you've established one step in your supply chain, you don't revise it. So in terms of like software, which I'm going to jump analogies here, software, like first you write of all the requirements. And once that's done, you start implementing them. And then you come up with a bunch of features. And then you do a release. And you don't go backwards in that process. That's the waterfall model of software engineering, which actually most people say they don't like and they tend to not follow. But it does exist as a thing to talk about. So why am I talking about this stuff with feed-forward neural networks? So again, this is a weird episode in that we're going to talk about what we're not talking about. Because in the future, I'm going to break this rule. We're going to talk about when there's cycles in neural networks. But it's important to have a foundation of the definition of a feed-forward neural network. And that's one in which the information only goes from left to right. It only proceeds in a linear fashion through the nodes. So last mini episode, we talked about the perceptron, the sort of like atomic unit of a neural network or of many neural networks. So a perceptron is like a single layer neural network. It's the base example. So you have some inputs, they are weighted and summed up, and then if they're greater than some activation value, usually 0, you say, hey, this is on, it's a +1. And if they are lower than 0, you say it's a -1. And every layer proceeds in this fashion, summing up, weighting, and then comparing the final product to, is it greater than or less than 0? And then passing along their outputs to the next node. So it's a little bit like an assembly line, right? Everything goes left to right.
Yeah.
So I keep describing this limit we have. Why do we limit ourselves with this feed-forward neural network? Any thoughts?
To save time Money.
Actually, you're not far off. Keep going. I know you're just kind of guessing, but you're actually very close to
Well,
correct.
that's why project managers do it.
Saving time and money. Is there anything else you save?
Time, money, resources, everything.
What about convergence?
What does that mean?
How quickly you arrive at an answer. What about tractability?
What's that?
The likelihood you will find a solution if a solution exists.
It's called tractability?
That's not the definition of
I've
tractability.
never heard of that.
Yeah, something that's tractable can be solved. Something that's intractable, while it might have a solution, you can't find it in an efficient amount of time. So there's an interesting thing. We're not going to define it here, but I'm going to state it. It's called the universal approximation theorem. And that tells us that actually any mathematical mapping from some set of inputs to some set of outputs, as long as you have one hidden layer, you can definitely represent that knowledge. Now, that actually blows my mind. Does it blow your mind?
As long as you have one layer.
One hidden layer.
Then what?
Then you can represent any mathematical function.
I don't even know what that means, so I don't know how to represent a mathematical function, period. So no, it doesn't blow my mind.
Well, let's break it down. Let me show you first some truth tables here I prepared. Let me first give you this one. Can you describe what's on the card I handed to you?
It says and.
The name of this card is and, that's right. And below it is a truth table. What do you see there?
I see columns with zeros and ones.
Yep. So the first two columns, I1 and I2, are the inputs. And then what's the third column?
Output. It's made of zeros and ones. It has 3 columns and 4 rows.
And what does the output look like?
It says 0, 0, 0, 1 from top to bottom.
Under what conditions does the output go to 1?
Only if both inputs have 1.
Aha, that is the AND function.
So this is just a standard function name?
Yep, and it's kind of linguistical, right? You say something and, like today is Wednesday and we are sitting at the dining room table. That is truthful. Although today is Wednesday and we are sitting on the beach is not truthful. Even though one part is truth. Now here, for comparison's sake, here's the OR function. Can you now describe OR?
OR is a similar table, except now, as long as one of the columns have 1, then the output is 1.
So we might say that if input 1 or input 2 is 1, the output is 1.
Yes.
All right. Now below those, you see I've written a little algebra equation. Can you read that off?
Output is equal to W1 input 1 plus W2 input 2.
In machine learning, the classic problem here might be identifying what weights, what W1 and W2, would allow you to represent this mathematical function. So for the case of OR, if I just set the weight equal to any value greater than 0, right, for weight 1 and weight 2, if both inputs are 0, then it doesn't matter what the weights are, right? Some weight times 0 is 0, and then 0 plus 0 is 0, so you get the right output. But if either is not 0 and either weight is greater than 0, then you end up with a value greater than 0. But now let me hit you with the actually most tricky version. This is another type of logical operator. As far as I know, you're not a computer scientist, right? So let's see how you pronounce this. What is the word at the top of that index card?
XOR.
Oh, you did it right. Oh, wow. You should get right into a computer science program.
More women.
That's true. What do you think most people would call that?
XOR.
Yeah, XOR. Which I always thought would make a great superhero
I was just going to say, yeah, great for a comic book character.
XOR.
From the planet Xor.
Wait, why would his name be Xor if he was from the planet Xor?
Well, it could also be a planet like Kryptonite.
Okay, jeez, Linda. Okay. Krypton was the planet.
Oh.
And kryptonite is an element.
I thought Kryptonite was
Linda, get
the
it straight.
planet.
This is important. Yes, but back to it. XOR is what we call this function. Now describe the truth table you see on this index card.
If there is a 1 and a 0 in either of the inputs, then the output is 1. If they are all zeros, it is a 0. And then if both inputs are 1, then the output is now, drum roll, 0.
Aha, that's the tricky digit right there. That actually makes all the difference. So we call this XOR. What we might better call it is exclusive OR. This is more of like the colloquial definition of OR. It's this one is true if and only if a single value is true. See how that works? Mm-hmm. See the difference between XOR and OR?
Yes.
Now, the interesting thing here, you cannot represent XOR in a single layer neural network. Gasp. It's impossible.
Let's take a break from today's episode to talk about our sponsor, Periscope Data. For a while now, I've wanted to keep track of how many downloads Data Skeptic episodes are getting and compare them across recent episodes. Of course, older episodes have had more time to accrue downloads, so I need a way to easily line them up by days since download. My data lives in MySQL. I guess this would be possible to do with an import into Excel, but I really need a reproducible process. I want to review this every day and have it be up to date automatically. That's why I'm really glad I discovered the cohort table charting type in Periscope Data. With a quick query and a few clicks, I was able to align recent episodes by their age for a fair comparison. That actually happens automatically. You can check that out at our site and view a screenshot of this chart I made. Cohort charts are one of the many great features of Periscope Data. Of course, all your standard chart types are there, even sparklines for you Edward Tufte fans. If you've got experience with Python's pandas library, I guess you could create something similar manually, but the time to delivery and the ability to automate this made Periscope Data the obvious choice for my needs. Check out what they can do for you at periscopedata.com/skeptics. Once again, that's periscopedata.com/skeptics.
XOR requires 2 layers because you have to first check if both of them are true or both false. With that condition known, you can then look at the sum of the values.
How do humans do it?
Well, that's a little bit of philosophy and debate, I think. Presumably, we do it ostensibly in the same way that neural networks do it.
How many layers do we need?
We only need one hidden layer. Whether or not we're utilizing more layers to solve it is unknown. But that's actually a good key point here. Any mathematical function, given the universal approximation theorem, tells us that you can represent any mathematical function in one hidden layer. However, in deep learning, we tend to use a lot more layers because that benefits the learning process and how quickly you converge and things like that.
Well, also, maybe that's why it's called deep. There's so many layers.
Yeah. Wow. Say that again a little bit more like a pothead, though. That sounded really like a revelation of some kind.
No, you're recording. You'll just have to play it back.
Whoa. Maybe we'll go down to Venice Beach after this and we'll get someone to explain it. So anyway, the feed-forward neural network is still very powerful, and we're going to talk about in future episodes what happens when you relax that constraint and you allow information to flow backwards. But as long as you have one hidden layer, the trickiness of exclusive OR can be represented. And there are other functions just like that cannot be represented in one layer, but in at least one hidden layer. At least one hidden layer, you can represent them in a neural network. So we're either going to call this episode XOR or feed-forward neural networks. These two concepts seem to overlap pretty well. So we're building blocks here. We talked about logistic regression a bit ago, which uses an activation function. And we'll talk about activation functions in a bit, I think, in one episode. That might be good to do a whole show on. But the perceptron we talked about last time is the core building block. And when you assemble a bunch of them, you can make a single layer neural network, but it's not quite expressive enough. You need at least one hidden layer to represent more complicated mathematical functions. And if you add a bunch of layers, for whatever reason, empirically, you're able to converge and solve things a little bit faster and more efficiently. How many layers do you think are in the human brain?
I was going to ask you that. Well, I feel like you probably can't count it. Because I think we fire all our neurons at once.
But don't we only use 20% of the brain?
Well, I don't know. Actually,
not true.
Not technically at once. Because I think when they put us in an MRI, they could see certain things light up.
Yeah.
But they're all like cross-functional. So you're not actually sure if they're one layer or multiple.
That's a really good point. And actually, I should point out that neural networks, the kinds that I work on, are only loosely inspired by the human brain. Like we definitely, like the creators looked at the brain and said, oh, that seems to be how neurons work. Maybe we can make a data structure that represents that. But just because it was inspired by the brain doesn't mean it at all represents the brain. The brain may be working in different ways. I mean, there's no reason from a mathematical perspective to think that the brain is doing anything that a neural network can't do. but it doesn't mean they're doing it in the same way.
Well, maybe they shouldn't have named it neural networks.
All right, well, let's invent a time machine, go back to the 70s, and
That's
help
a
them.
misleading term.
Yeah, that's
now
true.
that if your statement is true, then this naming convention is not right.
Would you prefer the term ANN, artificial neural network?
Yeah,
Okay, well, that is around. All right, people do say that.
that's a better term
All right, well, we'll use that term on this podcast.
because
That's
it's
better.
made up anyways.
That's true, yeah, it's artificial.
Yeah.
All right, so from here on out, ANNs and deep ANNs, I guess, as proclaimed by Linda.
Now I just have to remember what it stands for.
But no, you're right. They're all artificial, and these neural networks only are loosely, let's call them, inspired by the human brain. Maybe they'll be better than the human brain. Who knows?
One day.
Yeah, one day, exactly. Well, until that day and until next time, I just want to remind everyone to keep thinking skeptically of and with data. Good night, Linda.
Good night, Kyle. Data Skeptic is a listener-supported program. To support the show, visit dataskeptic.com and click on the membership tab.